Hi, so this is the introduction of our MEMS capacitive pressure sensor. The components of the device are silicon substrate for base, air gap for the capacitor medium, top and bottom electrode as the parallel plate for the capacitor mechanism, as shown in the right figure. Next, the top electrode variables that being analyzed using ANSYS software are thickness of top electrode and material, which is aluminum alloy, copper alloy, magnesium alloy, and titanium alloy. Meanwhile, the bottom electrode is fixed using the aluminum alloy.
By using ANSYS software, first, right-click Geometry panel to open Design Modular and design the device. Next, after saving the design, then double-click the model. After that, we assign the desired material and generate the mesh. Next, double-click the static structure. We insert the fixed support for the device. Next, double-click again at the static structure, and then we assign the input pressure. The input pressure value is different for each material. Next, double-click the solution and assign output deformation for total deformation object. The output capacitance obtained by calculating using formula based on deformation length. Finally, we click Solve to get the result.
The design MEMS capacitive pressure sensor is constructed by the titanium top electrode, the aluminum bottom electrode, and the dielectric layer. The titanium is flexible while the aluminum is fixed. The working principle: the top electrode will deform with the pressure applied. The gap between the electrode will reduces, hence the capacitor increases. The simulation uses the finite element analysis. The applied input is the pressures. The also output is the deformations. From the deformation, the capacitor value can be obtained through this equation. From the graph can be shown that the capacitor increases with the pressure applied. When no pressure is on the top electrode, no bending occurs, hence the gap is maximum. The capacitor value is initial value. When the pressure is applied, the titanium bends over the aluminum and the gap reduces, hence the capacitor value increases. In conclusion, the sensor increases the capacitance with the applied pressure.
Good day everyone, I'm Alpha Bentis Bairi from MEMS01. In this presentation, the metal alloy assigned is copper, so this is the animation on how the capacitive pressure sensor will work in ANSYS software. There are two different thicknesses used at the top electrode of copper, whereby 3 micrometer and 1 micrometer. At 3 micrometer, the input pressure is being set up to 28.5 exponent 9 Pascal. At 1 micrometer, the input pressure is set up to 2.6149 exponent 9 Pascal. When the pressure is applied, the deformation occurs. Deformation and capacitance are dependent to the pressure. Maximum input pressure is assigned to get a maximum deflection of 5 micrometer membrane. In short, when the thickness increases, the pressure will be increased. When the thickness decreases, the deflection of membrane will be increased. Thus, it is also will increase the sensitivity of the device.
Good day, my name is Lia Hui-yin. I used magnesium as the flexible membrane. Air gap between the top electrode and bottom electrode is 5 micrometer. Firstly, I used thickness 3 micrometer of the magnesium and deflection shows in the left hand side video. It needs 1.2 times 10 power of 10 Pascal of pressure in order to achieve the maximum deflections. Next, I used the thickness 1 micrometer and deflection shows in the right hand side video. It needs less pressure, which is 1.1 times 10 power of 9 Pascal. The table shows the comparisons of the thickness between 3 micrometer and 1 micrometer. As conclusions, the thinner the magnesium, the more membrane deflect. Second, 1 micrometer needs less pressure compared to 3 micrometer in order to achieve the maximum deflections. Third, the capacitance is directly proportional to the pressure. Fourth, the thinner the magnesium has the higher sensitivity. Lastly, MEMS capacitive sensor with the thickness 1 micrometer is more sensitive than 3 micrometer. Thank you.
Hi, my name is Mama Iman Azri. I'm using aluminum alloy as the top electrode. This animation of the ANSYS simulation. There are two thicknesses of top electrode are being analyzed. First is 3 micrometer and second is 1 micrometer. Next, it shows the table and graph of the analyzed result. From the result, we can obtain the input pressure range, where the range that the device can work. For the 3 micrometer thickness, it works up to 2.7833 exponent 10 Pascal, while for the 1 micrometer thickness, it works up to 2.3512 exponent 10 Pascal. The maximum work pressure range is where the top electrode deforms to the maximum thickness of air gap. The conclusion from the analyzed result, we can say that if the thickness of top electrode increase, then the maximum pressure value of work range also increase. However, if the thickness of top electrode decrease, the sensitivity of device are increased.
This is the application for COVID-19. For a COVID patient, the COVID-19 patient's lungs is getting a huge impact from the disease, where have caused the decreasing in strength of the lung itself. The respiratory system throughout the inhale and exhale process must be examined in order to make sure the lung is functioning well. At first, by monitoring using a simple Magnesium device. This device of MEMS capacitive pressure sensor can be applied in the COVID-19 application in order to produce a monitoring advanced technology device which is more precise and effective. The exhale strength will deflect the membrane of this device, which is the top electrode, and the capacitance difference will be obtained. The value can be monitored in order to monitor the COVID-19 patient exhale strength. That's all. Thank you.